Hey everyone, it's Mr. Glover here. So today the topic's going to be something called compound interest. Yesterday we talked about simple interest. And compound interest is a similar idea, but there's some minor differences that end up being really, really major differences when you actually crunch the numbers. So let's talk about it a little bit. So far we've discussed simple interest. With simple interest, you will always pay a specified percentage of the original principal of the loan. This means you will always pay the same amount of interest. So for example, you take out a $100 loan, 5% interest, you will pay $5 per year until that loan is paid off. Well, this makes sense for small loans, which are paid back over short periods of time. It isn't ideal for something like a mortgage. For example, let's say that you took out a loan for $100,000 to buy a house, and it was 3% interest. That means you will pay $3,000 in interest every single year from the start of your mortgage to the end of your mortgage. And if you add up the amount of money you're paying, that quickly starts to become an extreme amount of money. As such, most of the financial world uses what's called compound interest. With compound interest, principal of A0 is invested at an annual interest rate of I. This interest is then added back into your principal, known as compound. After a given amount of time, known as the compounding period, we can create an exponential equation to solve for the amount of money available after t years. So before we talk about the equation, this concept of compound interest is that there's a period of time, and after that period of time, your interest is calculated. But it's not the whole interest, it's only a portion. So let's say your interest is calculated every month. Once a month, you'll get 1/12 of your annual interest. That gets dumped back into your bank. And then the next time that you have interest calculated, you will earn interest on the interest you've already earned. So let's do the $100 example. Let's say that you invest $100 at 5% interest. Once you have compound, we'll do it once a year. Once a year, you're going to get $5 out of it. So then the next time you have interest calculated, you'll earn 5% of $105. So you'll earn, I don't know, maybe $5.50 or something like that. Something slightly more than 5. Then the next year, you'll earn compound interest on $110. And so it doesn't really seem like a lot, but you will earn interest on interest. And over time, this becomes extremely powerful. And we'll go through some calculations on this. So let's talk about the formula. If a principal of A0 is invested at an interest rate of I, with n compounding periods per year, the amount A dollars will be available after t years. So we've got 4 variables here. We've got A0, that's the principal. We've got I, which is the interest rate. Be really careful. You can't just type in, you can't just punch in 6%. You have to divide by 100 still. N is going to be your number of compounding periods within a year. T is the number of years, and A is what you call the future value. This is how much your money will grow to after the term has expired. So let's take a look at some questions. Last summer, Hunter got a job at a grocery store and managed to save $10,000. He decided to invest it in a college fund for the next 10 years while he goes and travels. He wants to get a math degree afterwards. Find out how much he will have if it grows at 6% interest compounded annually. So before we start the question, we've got to unpack the question and write out what we know. We know he started with $10,000. That is his principal, so A0 equals 10,000. He decided to invest it in a college fund for 10 years. So T equals 10 years. He has 6% interest. So I equals 6%, 0.06. That's 6 divided by 100. And it has compounding annually, so there is n equals 1 compounding period in a year. What we don't know is A. Okay. So we start by listing out the formula. A equals A0 times 1 plus I over n to the nt. And we put in what we know. So we know A0, that's 10,000. times 1 plus 0.06 over 1 to the power 1 times 10. You can either punch this in your calculator now, or you can simplify it. So this could simplify to 10,000 times 1.06 to the power 10. And now we can put this in our calculator. And so after 10 years, Hunter's $10,000 has become oh, no, sorry, I made a big mistake. Let's try this again. Okay, so after 10 years, Hunter's $10,000 has become $17,908 and 48 cents. That's quite a lot more than $10,000. Now, it doesn't really seem like a lot. He's only made $7,000, but you have to remember he's made $7,000 by not doing anything. He's literally just parked his money in a bank account, and that bank account is earning him interest. And he's managed to almost double his money in 10 years. That's pretty good. Now, the cost of living is going to go up. 2% roughly is what inflation is. So his 17,900 might not be as much as it would have been 10 years ago, but it's a whole heck of a lot better than $10,000 today. Let's take a look at an extreme example. So Jordan sells her old pre-calc 11 notes online and makes $50,000. They're very sought after. She chooses to invest it in a retirement account for 50 years while she works. The investment that she chooses pays 12% interest compounded annually. How much money will she have for her retirement in 50 years? Now, this is a really, really smart decision. And I mean, most people don't have $50,000 to just stick in the bank, but if you do, and you don't need to use it, you can set yourself up for life by making a choice like this. Before we do the question, I want you to think in your head for a second. Think about what you think the money is going to be worth. Is it going to be 100,000, 200,000, 300,000? Is she going to be a millionaire? Okay. Think about that number. Now let's do the math and see how much money this actually is going to be. So we've got to unpack the question. A naught is 50,000. She chooses to invest in retirement account for 50 years, so T equals 50. The investment she chose pays 12% interest, so I equals 12%. 12 over 100 is 0.12. And it's compounded annually, so N equals 1. You don't know A. So we start the same place as last time. A equals A naught times 1 plus I over N to the NT. Put in our numbers. A naught is 50,000 times 1 plus 0.12 over 1 to the power 1 times 50. We can simplify this again. This equals 50,000 times 1.12 to the power 50. And now let's do this calculation. So that means that after 50 years, Jordan's money will grow to $14,450,109.49. No, I'm not kidding. That is actually how much money she's going to have. If you have money, making money is fairly straightforward. It's getting the money in the first place that's the hard part. If somebody wants to lend me $1 million, I'll gladly pay them back, but I don't have $1 million to throw in the bank account right now to invest. So having money makes getting money much, much, much easier. Now, there's a couple things we should talk about here. We'll talk about why this is unrealistic. First of all, you've got to have 50 grand, and you need to have not only have it, but you need to not be able to touch it for 50 years. You also need to earn 12% interest, which is not very easy to do. It's doable. You can do it in the stock market, but you're going to take risk, and you're not likely going to get that consistently for 50 straight years unless you're a very savvy investor. Realistically, I would probably use numbers like 6%, but you could do better than that if you make smart choices and you're willing to take on risk. But having said that, there's no reason why you shouldn't be a millionaire by the time you retire if you are disciplined and you make wise choices with your money. So let's talk about compounding periods. Not all investments are compounded annually. So these are some different things that you will see. These are all different compounding periods. These are real words that come up in finances all the time. Annually, frequency of compounding is 1 time per year. Number of periods per year, 1. Semi-annually, every 2 months. Or sorry, yeah, 2 months, every 6 months. That's 2 compounding periods a year. And maybe I'll write n equals 1 and n equals 2. The quarterly means it's every 3 months. And so n equals 4. It splits the year into quarters. Monthly is going to be every month. In this case, n equals 12. Bi-weekly is every 2 weeks. In this case, n is going to be 26. And weekly, I think that you know what that means, it's every week. And n equals 52. You can also have daily compounding and things like that. The message that I want to get across with compounding periods is that the more frequently your money compounds, that means the more frequently your money is growing. So even if you only receive 1/26th of your interest, it's still happening every 2 weeks. So you are going to earn more interest on your interest. So the more frequent your compounding periods, the more money you will make. It's not incredibly dramatic. It's not as dramatic as time is. It's not as dramatic as interest is. Those are the 2 driving forces here. But if you have a choice between 2 investments with the same interest rates, with the same term, but one of them compounds more frequently, pick that one. Likewise, if you're paying off debt, the more frequently you make payments, the better off you'll do. And it's not going to be thousands of dollars, but you might save yourself a bit of money. If you're able to pay your car payment bi-weekly, you'll come out ahead than if you pay it monthly. Not a lot, but a little bit. So let's take a look at this. $23,000 is invested in an account that earns 13.6% annually, compounded semi-annually. Find the future value of this investment after 5 years. All right, so list out what we know. A0, our principal, is $23,000. Invested in an account that earns 13.6%, so I equals 0.136 annually, compounded semi-annually, so n equals 2. And this is 5 years, so t equals 5. What we don't know is a. So we start with the same formula. A equals A0 times 1 plus I over n to the nt. Zoom in a little bit. We'll put in our numbers. A0 is 23,000 times 1 plus 0.136 divided by 2 to the power 2 times 5. And now you can punch this in your calculator right now, or you can try and simplify it a little bit. I'm just going to calculate those brackets. So 1 plus 0.136 over 2. This equation will simplify into 23,000 times 1.068 to the power 10. Now we can do the whole calculation. 23,000 times 1.068 to the power 10. And after 5 years, this $23,000 turns into $44,405 and 87 cents. Now, this has a really high interest rate, so the doubling time is going to be fairly short. But this concept I want to get through to you, and this is a really important concept, is that the sooner you can double your money, the sooner that money doubles, and then the sooner that money doubles. So because this is increasing in an exponential way, it's not going to a slight advantage in the start. And if you have time on your side, that's a huge advantage. Slight advantage in the start compounds into a huge advantage by the end. If you start with 23 and you can turn that into 46, then you can turn that into 92, then you can turn that into 184. And if you keep doubling, $1 million turns into 2 million, which is turned into 4 million, which is then 8 million, which is then 16 million, which is then 32 million over the same periods of time. So time and interest are the two most important factors, and time is what most of you have on your side right now. All right, let's try solving for something that's not future value. Tanis wants to save up to buy herself a new car. She sets a budget of $5,000 and wants to reach this goal in 5 years. She chooses an investment that pays 5% interest compounded quarterly. What principal does she need to invest today? So the only difference here is that 5,000 is not your principal, that's your future value. So A is $5,000. We don't know A naught. A naught is unknown. We have 5 years term, where T equals 5. She chooses an investment that pays 5% interest. I equals 0.05, compounded quarterly, so N equals 4. What principal does she need to invest today? Okay, so let's set up our equation. A equals A naught times 1 plus I over N to the NT. And now we aren't solving for A this time, we're solving for A naught. So we have to do some rearranging. If you're more comfortable, you can plug in your numbers first, simplify it a little bit, and then rearrange. But if you want the most precise answer, you need to plug in your numbers all in one shot, because otherwise you'll be rounding. And when you round, you introduce errors. So I'm just going to move everything except for A naught. Fortunately, this entire term here can be treated as one thing. So we can divide it as if this was just X. So I can take A, and I can divide A by 1 plus I over N to the NT. And now I've got this expression solved for A naught, or the principal. Now I'm going to plug my numbers in. A is 5,000 divided by 1 plus I over N. So this is 1 plus 0.05 over 4 to the power of 4 times 5. And now you can plug this in your calculator all at once, or you can try and simplify it. Now, simplifying it, you might end up rounding and you might end up with less precise results, but see what happens. So I'm going to try and simplify my brackets. 1 plus 0.05 divided by 4. And I end up with 5,000 divided by 1.0125. It's the power of 4 times 5, which is 20. This is something I'm more comfortable putting in my calculator. So $5,000 divided by, make sure that you put brackets around your denominator and you don't accidentally put the whole thing to the power 20. So 1.0125 to the power 20. And Tanis would have had to have an investment of $3,900.04. $3,900.04 equals A naught. So what we just did is we just worked backwards and found out how much money needs to be invested at that specific interest rate for that specific term to get to $5,000. This is this is sort of what you need to do for your retirement. You need to target a goal for how much money you want, and that depends on what kind of income level you want, and you need to figure out a plan to get there. Now, most of the time, people don't have 100 grand to dump in the bank account at age 18. So usually you're going to have payments involved, and we'll talk about how to incorporate payments later. But you do need to have a plan, and the sooner you start prepping for it, the better off your future is going to work out. Trust me on this one. You don't want to wait till you're 30 or 40 to start planning. It seems like a long ways away, and it is. I mean, if you're 18, you're looking at 47 years before you retire. That's the standard age. That's kind of a sobering thought. But if you can plan now, that's 47 years that you can now use in your favor with compounding interest. So let's talk about some estimation tricks. The rule of 72. This is a really useful tool. It's a simple formula, and what it is it's used for estimation. So the rule of 72 is a formula used to estimate the time required for an investment to double. To use the rule, divide 72 by your annual interest rate. This will be approximately how many years are required to double your money. This is a huge, powerful tool because you can quickly ballpark doubling time, and it shows you the difference between interest rates. So, for example, if you take 72 and you divide it by 6% interest, that gets you 12. So that means if you have 6% interest, your money will double every 12 years. Let's just change that slightly. Let's change that to 8%. 72 over 8 is 9. That means your money will double every 9 years. And that doesn't seem like a lot, but if you have 47 years, you want to double your money as many times as possible in that period. Because the last time you double is where you make the most money. If you're doubling from 1 million to 2 million, that's a huge difference. If you're doubling from 5 million to 10 million, that's a huge difference. And you want to make sure you get that last period of doubling. So interest rate is huge. If you had something like 12%, 72 over 12 means that your money doubles every 6 years. So you will grow your money very quickly if you can maintain that high of an interest rate without losing money. So let's put this to the test. Bolton has $500 to invest in an account that pays 6% annually compounded monthly. He has $1,000 to buy, or he needs $1,000 to buy textbooks for his first year university courses. So we don't really need to set up our equation for part A. We just need to estimate. So if he has 6% interest, 72 over 6 is 12 years. So his money will double in approximately 12 years. And I mean, it doesn't seem like a lot, but that's any amount. You can double 100, you can double a million, you can double a billion. The more you have, the more the doubling will help you. Like I said, having money means making money is quite simple. So let's talk about how to actually find the exact time. And this is tricky, and this is technically something that you won't be able to do by hand precisely until grade 12. But I'm going to show you a strategy. So let's put in what we know. We know A equals 1,000. We know A naught equals 500. We know I equals 6%. Compounded annual or compounded monthly, so N equals 12. And we need to solve for T. Okay, so let's just plug this into our formula. A equals A naught times 1 plus I over N to the NT. Put the numbers in. 1,000 equals 500 times 1 plus 0.06 divided by 12 to the power 12 T. And now we can do some simplifying if we want to. And I suppose we should. Let's simplify the brackets, but you don't have to. You can plug this into a calculator as is. So 1 plus 0.06 over 12. It gets a little bit nicer. maybe we go 1,000 equals 500 times 1.005 to the 12. What I'm going to do is I'm going to use graphing technology to solve this. You can do it by hand, and you can use guess and check by testing powers of 1.005 until you get close to the number on the left. But that's not the way I want to do this. What I'm going to do is I'm going to take the left-hand side and I'm going to graph it as one function. Let's call it y1. I'm going to take the right-hand side and I'm going to graph it as a second function. I call it y2. And then I'm going to figure out where they intersect. Does that satisfy? That's the solution to our equation. So let's switch over to Desmos. First function is 1,000. I should probably say y equals 1,000. Second function is y equals 500 times 1.005 to the power 12x. And I don't know if you can do t. It might let you graph t, but it knows how to graph x. So now you're probably wondering why you can't see it. And if you only had a graphing calculator at your disposal, this is a little more annoying. But since we don't have a restriction, we can just zoom up. My money starts at 500, I need to get it to 1,000. So I need to go to at least 500 on the y-axis. So I need to zoom out a lot. 1,000 is where they're going to meet. Right here is where they're going to meet. So 11.581 is the exact point in time when you'll double your money. So 11 years, 11.581 years, slightly less than 12. So the rule of 72 is not exact, and it's going to depend on things like how frequently your money is compounding, but it's a good estimate. We guessed 12, and the answer was 11.6. So I suppose we should go back to our notes, finish this off, 11.581. Yeah, 11.581. So we're going to graph, find the intersect. The money doubles after 11.581 years. Right now, that's going to be our best strategy for solving for time. Guess and check is another option, but until you learn about logarithms, which is a grade 12 topic, you won't be able to solve exactly that. So that's where I'm going to stop things today. I've got some questions for you to try. They're based out of the workbook, page 630, questions 1 to 3, 5, and 10. 14 is an interesting question. It's about credit cards and their compounding periods. If you've got the time and you've got the interest, you can try it, but treat it like a bonus question. It's just an extra question to give you a little bit more practice. So I'm going to end the video here. I hope everybody has a great rest of the day, and I hope to see you all in our meeting tomorrow. Bye for now.